Yeah, today we have the first lecture is by Junwu Tu from University of Missouri, and he's talking about homotopy L-infinity spaces and mirror symmetry.
Thank you for having me here. It feels very good to be in Boston, where the true American spirit is. Like I always be in the Midwest, and kind of people are more lazy there. When I come here, I also start to work. So I will talk about homotopy L-infinity spaces. So, but I was really kind of tell a story how I get to this notion from considering family of Lagrangian cloth theory. So I begin with the setup of a Lagrangian torus family like B, and this is allowed to be singular fibers, so you can get generality, not even a mid section. But then I will quickly say I'll only look at the smooth slopers. These are the vibration, the part of the vibration which fibers are all smooth torus. And actually, I will look at even just an open subset here, B. Not the whole smooth sloper. Still denoted by pi. And to be even more concrete, I just look at one point. So I fix one point in this open set. And fiber is torus of P. So the picture that I had, the question that I had was the following. So I'm a more algebraic person after PhD, so I was just looking at L-infinity algebras. But then I was considering, of course, this so-called Pi algebra. So I did not Pi or it's just the self-X in the Fukaya category of this Lagrange. So this one is an L-infinity algebra. Now the question is how this A-infinity algebra change with I was hoping, so before I started with this problem, I was hoping to get something like a family of A-infinity algebra over this open subset B. So actually it is the case. So the simplest case possible is the. So let's look at this situation. And there is no holomorphic disks bounding L of any phi. Okay, so if you assume there is no holomorphic discrete boundary lying on this Lagrangian for every fiber of this family over B, then it's very classical. It's known that this Fukaya algebra. So let me put Q. P is a fixed point. Q is a general point. But this is just the cohomology of the torus. It's just ordinary cohomology of torus. And now we have this is a vibration. So locally, this vibration, we can trivialize it locally. And I choose a place special point P, so I will trivialize everything to the same vector LP. So if we choose a trivialization, then we actually get a family of algebras. It's just actually ordinary algebra, not just cut product. So what I just said here. So what we're looking at is family. Usually people say it's pi r pi lower star of the. Let's say I choose complex coefficient. So I have a complex local this C sheaf, constant sheaf here, and the push forward, derived push forward, I get the homological fiber. And this is actually a trivial. After trivialization, this is just considered as a constant sheaf on the. So actually here, if there's a observe that there is a Gauss-Manning connection, right? On this family. And it's very nice that because this is it's actually a constant family of algebras. So if you differentiate, these are flat sections of this constant connection. So if you differentiate this M2, now you consider this cut product as a family of multiplications on this local system. And you differentiate this multiplication, it's 0. So in this classical situation, it's very nice. We get, if you want, a flat family of L-infinity algebra, but it's just the ordinary relationship algebra. Okay, so now that's what I actually begin with. Then I thought maybe this is true in general with this L-infinity structure. So to talk about that, let's pick coordinates. So actually, there's a special thing about being a torus fiber, namely this one, of course, we know it's just the exterior algebra generated by H1. This one. But actually, it's a special situation. So we have this torus vibration where the tangent of the base can be identified with H1 of the fiber. This is like the Caldera-Spencer. Right? H1 describes deformation of the Lagrangian, and we got the family of Lagrangian. So this, if you choose a basis, okay, so this can be thought of as I'll just write E1 N, where I choose a basis where the span of E1 En is equal to H1 of LP with integral coefficients. Okay. So these are flat sections. And then, as I said, this one actually can be viewed as tangent vectors in the base parameter. So I'll just write partial QJ. So this is the tangent. Or like in a Conan stock, these are affine coordinates in the base. Give a fiber direction H1. Okay, let's write down this multiplication. So the entire multiplication look like, I'll put a Q here so that you see it depends on the parameter Q. And then I have this, I'll just look at input being this E1. EK, I1. So it's defined like this. Over beta, where beta is a relative homotopy class. And then we have M3 beta still depend on Q of E1, I1, okay. So this is operator I'll explain this very soon. And then there is a coefficient here, e to the power minus beta. So line 2 class. So we evaluate that area. Of course, there's convergence issue. So if you really work on this, it should be not be called T, but just this. Okay, so what is this MK beta? Okay, there's this moduli space of K plus 1 multiples plus beta, and boundary lies on this Lagrangian LQ. And to talk about the moduli space, we need to pick a almost complex structure J. And then we look at this moduli space of maps from holomorphic disk. So when K plus 1 multiple is on the boundary, there's 2 in this case. Then you look at the set of holomorphic maps, 2 and L. So it's not correct, but that's all I know. So I'll do like this. So there are K plus 1 evaluation maps, right? So they are on the boundary. I'll keep this one. So these moduli spaces has evaluation maps to the Lagrangian K copies. And then there is the index 0, and it's 0 1 that maps to the Lagrangian again. So what we do is we have these differential forms on the torus. Then you pull back by the evaluation map to the moduli, and then you integration along fiber. So this evaluation 0 to get this. So that's this operator. Of course, there are this space is not smooth space. It has this condition structure that you have to deal with. A lot of work has to be done here. But let's assume that that's done. Now, so then I actually asked Garrett, who gave a talk on it, and then he told me that this is not going to work because it's never going to be a family in general, because you have this picture. He gave me an example where you have this V here, and then you have a one parameter family, L0, Lt, or T small. And now what you can have is these modular spaces. I'll just write one and forget about it. This is going to be non-empty for L0, and this modular space is equal to empty at Lt. So you could have a one parameter family of Lagrangian where there's only one fiber where this actually is non-empty set. And then all the other Lagrangians in this family have empty. There's no holomorphic disk. So this is bad because if you have this situation, this operator is not even continuous, has not continuous dependence on Q. So we cannot even differentiate like in the case of non-holomorphic. So now how do you solve this problem? So fortunately, Fukai already actually solved it. Not it. Probably he also thought about this situation. So he just this trick. So I call it Fukaya's trick. So it's called a trick because you kind of solve the problem with no effort. So what he does is very smart. So look at this modular space. And remember, I actually fixed the point P in the open subset. And then I choose J. Now here observe that this Fukaya algebra itself, the very construction of the infinity structure depends on a complex parameter J. So this J holomorphic curves. So this J. So then what his idea is to use different J for different fibers. So if I have another fiber, so I have LQ. I use a different J, and how do I get that different J? I choose so the picture, just show the picture. So I have this P point here fixed. I have a holomorphic disk here. So the boundary lies in LP. Now what I can do is I can choose a, so this trick is to choose an isotopy. Just notify P PQ from N to N. It's only a diffeomorphism, so it will change the symplectic structure. But it has the property of sending this LP to LP to LP. Another property you want is so that we'll use this P lower star J. So this is what I will put here when I consider J holomorphic curves on the LQ, with this on the boundary of LQ. So you want to be able to do flow theory here. So this has to be also a tape, omega tape. Almost complete. So you want some positivity. That's all you need to do flow theory. And if the class is just here going to be just Q lower star of beta. And there is actually isomorphism just by pushing forward by this diffeomorphism. Whenever you have a map, so the picture is whenever you have a holomorphic disk with boundary line LQ, you post-compose with this diffeomorphism, you end up getting a holomorphic disk with boundary line LQ. So that's his idea, and so of course, whatever you do to do a solve transversality problem, it should be use the same structure where you have this kind of pushing forward by diffeomorphism. Okay, so that's the idea, and now if I do this, let's see what happens when I have this much validation. So now what happens is these modular spaces are actually the same under this pushing forward. Okay. So if I look at these differential forms, where I also pull back the differential forms, right, under this diffeomorphism. But then for us, if we choose this remember these are flat sections of the local system relative to this relative to homology, right, on each fiber. Under isotopy, they are flat. Isotopy does not change integral class. So actually these EIs are just these sections again. So what we are saying is if I perform this calculation, differentiation, so I just, let's say, I differentiate in the QJ variable of this multiplication. So what I will get, so this theta I will sum over just phi 2 of m LP. Okay. So even though I look at MQ, I look at homological class in P. And then I just put MP here. Okay. Because this part of the in MK, it's the same for every Q because of that reason. And now what changes this is this area part. So I'm just going to differentiate. This is constant in Q. I just want to differentiate partial Qj. Sorry, so there's no equality here. MK beta. That's beta. I just want to differentiate this area. So it's phi dq lower star beta. So now I can actually differentiate. So previously, if I used same complex structure, this is discontinuous function. But now if I move the complex structure according to the Lagrangian, this is constant. Now, of course, this is actually analytic dependence on the base parameter. It's just exponential. So let's see. So I still have the picture here. So we are differentiating the symplectic area. And now we know differentiating area of the disk. You just get the circumference of the disk. So what you will get here is this equal to MK beta B1 BI1 BIK and the same thing here. Now the derivative of this one becomes so the circumference is given by partial beta. That will be the boundary of the disk, and we evaluate. Remember, there's identification. If you differentiate in the Qj's coordinate, Qj gives you a H1 class fiber. So evaluate Ej. So this is the derivative of this Mk with respect to the base. And now it's we use another theorem, a theorem of Fukaya, which says some kind of cyclic symmetry. When you have this length here, you can actually put it in here. Namely, it's beta. And if you put one more marked point, and we insert Ej in all the possible places. And that is, so this is the formula in the cyclic symmetry of Kai. So what I want to say is that this gives a very nice, the sum is over insertions, not just beta, but also insertions of Ej. Now this gives a very nice formula, just an algebraic formula. Now we can get rid of beta. This is by definition Fj plus 1. I1 Ej Ik summing over insertions. So if you look at the formula here, what we get is this one is equal to that one. And this is just now algebra, and that's what I like. So there's no holomorphic. So you can talk about this kind of algebraic structure without any holomorphic pieces. So this is an example of L-infinity space. Actually, in this context, it should be called A-infinity space. It's a family, compatible family of A-infinity algebras.
You never use the big Torah.
What?
You never use the big Torah.
I used it because I used identification.
No, because B is not the base. I mean, B is just H1, basically. You just look at the modularized space of the branch. That's
Yeah, I think
the branches is only about whether that flow the comodules match product of H1. Just look at any modularized space of the branch.
so I need what you need is a map from the tangent space of the base to H1.
That's always true.
I think you can do this
The
structure.
base space is just modularized space of the branch.
Yeah, I agree. You can do this structure in a more general sense, but probably like a Lie algebra is.
No, just look at
Because you need to talk about the round, because of differentiation.
with respect to the modularized space of the branch.
Yeah. Okay, so let me put the conclusion here of this discussion. But now we have this smooth open subset in Rn, and then we have this a bundle of A-infinity algebras. Right, A. So A in this our example would be as a bundle, it's trivial bundle. It's just given by the homology. So we have this A-infinity algebra bundle. We have a connection here. This is the Gauss-Manning connection, naturally there. And now the formula we get is if we differentiate in the J's coordinate, the invariant way to write the formula is taking commutator because these MKs are multilinear maps. And this is the same as insertions of EJ, where we have this one more point. That is the conclusion. So again, here I'm using this identification between tangent in the base and degree 1 part of the A-infinity algebra. I use the fact that the degree 1 part of the A-infinity algebra, which is H1 here, is the same thing as tangent. Yes, so that's now, actually, this is the definition that I gave in one of my papers, the early paper. And then I discovered that Costello had another notion called L-infinity space. So actually, the two are very it's related. And it's a cleaner way to, it's a better way to see the same structure. So what he does is his idea is to look at the round complex. So you see A has a connection. So we can look at this curly A, which is the round complex of A. Because A has got a Gauss-Manning connection. And if you put, so this is an A-infinity structure. Now in this curly A, if you put M0 to be, or you can have one tensor M0 of this algebra bundle, but then you add another part, which is given by EQJ tensor partial Q2. In this notation there is given by EJ. right? Because the tangent, the degree 1 part, is the tangent. Okay, so this is a independent of coordinate. It's the Euler.
So what is A now? A is
A is this, which means the curly A?
no, just
This A is this A-infinity algebra bundle.
okay, still the same context.
What?
So still the same. Don't change the context.
So it does not have to be in this case. I'm talking about maybe abstraction of the structure we get from the family.
So arbitrary A infinity algebra.
Yeah, A is an A-infinity algebra.
So you fix the P from the what point P is fixed.
Yeah, what is
So you choose some point.
to trivialize the local system. But here I will not talk about flow theory. It's just an abstract algebraic structure. There's a B smooth manifold. There's a infinity algebra bundle, and there's a connection. And I'm saying the better way to think about this structure is to form the de Rham complex of A, because we got the connection. And then I have this modified, right? This
The
one,
condition is V is inside A.
what?
The condition is V is inside A.
B,
Well, that's why we circle it.
B is not inside there.
V is H1. H1 is
Tangent.
part of A.
Tangent. B,
Yeah,
tangent.
local.
Yeah, that's right.
Well, that's why how you can draw this circle.
Yeah. So this is invariant. This is the Euler. So M1 is given by identity, the Rham on the left hand side, plus 1 tensor M1. M2 is given by just the usual M2 here, and then extend linearly on the differential form.
I mean, just mean 1 tensor M2.
What?
Just 1 tensor M2.
Yeah. So you only change M0 and M1, and MKs are all the same. 1 tensor. Okay, so then you can check that this lemma, this capital operator from an A-infinity algebra, if and only if the equations are holds. So, so this motivates the definition of Costello. So what is a infinity space or an L-infinity space? It's super simple. It's just an A-infinity or L-infinity space is a pair V and curly G such that V is a smooth manifold. And G is an A-infinity or L-infinity algebra over so usually we talk about A-infinity algebra over a field. But then we talk about A-infinity algebra over commutative ring. But this is something more complicated. We talk about A-infinity algebra over differential graded ring, namely the de Rham complex.
Did you use this Gauss-Manning connection when you define capital M?
So to form the de Rham, Right?
So it's in the A-infinity operation. Applied.
Yeah, this is
This trivialization.
I always think about in Rn, but in general.
So say this is the function for minimax space. Can
No.
space.
No.
The space. How do you
So no. So this is more general. This is a very restricted structure. That restricted structure, if you do this, it gives this more general structure, and that's what Costello defines. Just an infinity structure over the round complex. So what I will talk about, so this is more or less its definition. There are some technical conditions. But what I will talk about is slightly different, but I will talk about examples. Okay. Yeah, so what so Costello does not care if this G is, how does it look like, but so I always take G to be something look like tangent part of B to begin with. Okay? So this is the degree 1 part. So actually I always look at positively graded the infinity space of infinity spaces. And Costello does everything, no conditional grading. So then this is degree 1 part, and then there is degree 2 part, and so on, of finite rank. So you stop at some.
So you're assuming that it's not just L size, that you get local space. Unless you don't pick up as a bundle.
Sorry?
You're assuming that that is locally free.
Yeah, locally. Vector bound.
But Costello is not.
Also locally free. Yeah.
Oh, so
Yeah. Yeah, you never talk about sheaves on space manifold.
Yeah.
Usually vector bound does on space manifold, not coherent sheaves on space. Okay. Yeah. So we already seen this example from family philosophy. Right? This is how we get the structure. This is how we arrived at the structure. Now the second one, the mirror statement. You can look at moduli spaces.
we also have G0, which is just C, right? H0 of T is C. H1 is
Yeah, so I usually forget about it. So you just delete the part. Right? Positive part is a sub infinity algebra. Okay? So I don't want to check those. There's a reason for it.
it's a pity of box.
Yeah, just so in general, this is not like you might think that this degree thing is like randomly given, but it's really important, the degree thing. So it's actually all this derived algebraic geometry is all about being considering these degrees. So if you look at any Lie algebra G, 0, G1, and so on. So the negative degree part. So the idea is this will be the space part, and this including 0 will be the stacky part. So this is automorphism. That's why I always look at positive graded.
Just switch the sign. Oh, those are plugs. I thought it was
So I always start with degree 1 where it's tangent. Okay, let me give you examples to be more concrete. So this one is the mirror statement. So you have this moduli spaces of coherent sheaves. Well, not all moduli spaces of coherent sheaves, but you need probably stable, simple, enough. Right? This is because of this degree condition. If you have no stable, then it's too big of x0. Now, I will give you two more examples, class of examples. So I look at L-infinity space, where G is just given by the, well actually here it should not be tangent, there's the wrong part. This should be G. It's curly G including the wrong, right? It's not, it's over the wrong. So if G is just the wrong part, tensor tangent part. And again, this tangent part is in degree 1. So you might think you get something extra, but so there's so you can prove that this is just this. There's a unique such. So every such G is isomorphic. Any such spaces are isomorphic. So the way to see it is an L-infinity structure, you have the bar construction in this differential equation setting too. So the Chevalier-Ellenberg of this L-infinity algebra is quasi-isomorphic just to the structure sheet. So the point is this Chevalier-Ellenberg G is quasi-isomorphic to the Duron complex of the infinite jet bundle. So there is a canonical connection on the infinite jet bundle, and every such Lie algebra has isomorphic. This one is.
Don't you need to assume that V is simply connected or something? Yeah,
No.
You can't use flat bundle.
It's always the jet bundle of V.
Sorry, I don't understand. What's the statement in part 3?
So any two are isomorphic. So if you have a
I mean, if you so you can change V. Is that what it?
Oh, V is
no, sorry. V is fixed. Yeah, V is fixed. Just change the Lie algebra round. Any two such Lie algebra roundel. So I'm just fixing the underlying vector round. I'm not talking about the L-infinity structure. So the statement is any L-infinity structures over V are isomorphic. They are the same. So this theory of L-infinity spaces, so if you look at this positive part, you should really, it's kind of another approach to derived geometry. And the relation to classical derived geometry is by taking Chevalier-Ellenberg of this Lie algebra, which is a commutative differential grid algebra. And what this says is, if you only look at degree 1 part, then you just get the manifold itself. There's no complicated thing. So now there's a more interesting example. That's the example that I will be focusing on today. Not too much, but I'll try to demonstrate with this example that this structure is useful to consider. So if you consider just some open subset V Rn, and you consider the trivial rank M bundle over V. So I'll look at, I'll first look at, just like in the floor theory case, I'll look at straight G, which is just the bundle part without the round this direction. I take the tangent part, which is just Rn. It's trivial, right? Everything is trivialized. So this is the tangent of V, this is the obstructions bundle, what we call obstruction bundle. So this is degree 1, this is degree 2. So I classify degree 1 case, now I want to classify degree 2 case, at least locally. Now you can show in this case what you get is just a section. So up to, so I'll actually give you the local model. Now you can describe this. So M0, the small M0, just like in the floor case, this is a section of the degree 2 part, right, by degree reason. So I'll use S1, that's what most people use, just for the Granition section. And the Lie structure, so if you think about it, this LK has degree 2 minus K. Okay. Now you think about how can it act on this degree 1 part and degree 2 part and be non-zero. The only part that's non-zero is given by you input K degree 1 element and get a degree 2 element. That's the only possible way to get non-zero multiplication. And very simple to describe what that is. Is given by the derivatives. Applied to the section.
L is what we used to call M.
Yeah. L is for the MK is for multiplication. L is for Lie. So it's very simple. So you have M0, and then you have M1, which is the derivative of the section, and then you have L2, which is the second derivative, and so on. Okay, so just like in the case of floor theory, you can define big M0. M0 plus this whole part. Then you have M1, given by the flat connection, everything is trivial, plus this derivative of S, which is acting on, this is a small M1, derivative. The M2 is just a small M2, sorry, I should use L, sorry. So it's just L2 and so on. LK is just LK, okay. So this gives L-infinity structure, L-infinity space structure, with curly G being the Durand. So actually you can prove that in this local case, that any L-infinity space with the underlying vector bundle given by 2 degrees, degree 1 and 2, is given by a section. Okay. So the structure, the point is 1-2 type L-infinity space is equivalent to what people call Granition charts.
Sorry. So what is the small g you're writing there?
Small g is the bundle without the Durand part, just like in the just the family of A-infinity structure in the floor case. And curly G is including the Durand part, horizontal part. Okay, so I mean the right. I think this is a little bit confusion to look at the wrong part. So I mean the right picture should be what we do here. Should be so I make an analog in the case of theory that you know. So we talk about vector bundles, right? And then we have this thing called flat vector bundles, right? So it's a vector bundle with a connection, flat connection. Plus a flat connection. And then we have this Durand complex. This is so Riemann-Gilbert correspondence, right? We have the Durand complex. put A-infinity or L-infinity structure here. So it's a vector bundle with this extra structure. Now, as we see in the flow case, it's not like all these higher multiplications are flat. There's compatibility between multiplication with the higher one more input, right? So this is the right structure to look at, and that's what we have this. That's what I have this A-infinity, L-infinity vector bundle plus it's a star equation, right? That was the compatibility for being flat. It's not really multiplications are flat operations. And then I can kind of
So this is what you call the space, right? Yeah, space.
No, this is the bundle with this constraint. So small mk, when you differentiate, it's equal to mk plus 1 of that n. I mean, this is the compatibility when you write in terms of the bundle method. But now you see the flatness here for vector bundle can be seen as just it forms a complex when you take the round. Now you can take the round here, and this is what we call A-infinity or L-infinity space. It's just a better way, I think, to pack this kind of data. It's more general than this data. Okay, so that is the structure. Okay. So I think next time I'll talk about how the structure. So remember, this structure, we get this structure by looking at a small open chart in the smooth part of the vibration. And now next time I'll talk about how to globalize this structure to the whole smooth chart. So now, what time do I have?
Yeah, so
Yeah, okay, so maybe I'll continue a little bit for this 1-2 type, because this is the important type. So this is the situation where you have tangent obstructions here, or to define virtual ground. And this can be used. And
So 1, 2 just means the G is concentrated in degrees 1 and 2.
Yeah.
That's it.
okay. So actually, most people, including me, call it 0, 1, because you see the tangent is got shifted. The tangent space should have amplitude 0 and 1, but then we shifted the tangent space. Okay, so this theory can be used in a concrete situation, and to identify the happening there. So using this kind of L-infinity structure, so namely we look at M, 3-dimensional, real-dimensional, integral homology. This means the homology of M with integral coefficient is the homology of M with real coefficient. Oh, sorry.
doesn't make sense.
That's 3. I slept too late last night. Coefficient. And we look at moduli space of representations on the momentum group into SU2. Now this condition, and I look at irreducible ones. Irreducible means there's no stabilizer. So the point of these conditions, these important conditions, integral homology sphere, and These two and SU2, not as opposed to SU3 or SU10, is a guarantee this is a no automorphism. That's all, and compact. It's compact space. It's not a manifold, singular, compact space, and no automorphism. No continuous family of morphisms. So local, you can put. It's true in general that if you have any, so you get this space as Monocartan moduli space. Looking at Monocartan equation of this the round complex of M with coefficient in SU2. So whenever you have this kind of situation, you have the elliptic operator. Then its Monocartan moduli space will be locally given this L-infinity structure. And the degree 1 part is the H1 homology. If you have any representation in this representation space, then the G, this Lie algebra bundle I'm talking about, at this point rho is given by H1 rho direct sum H2 rho. Now the fact is irreducible guarantees there's only H1, H2 and no H0, like on homological there will be no H3. So that is the situation we have in this example. So we see that locally it's just given by a section, and the map is given by potential. Now with this structure, people know, so this tells you that this by looking at this, you see that people know this is a pernicious structure. And there you can define a virtual cycle. This as an invariant is just by integrating 1 on the virtual cycle. In this case, again, by comparativity, the virtual dimension is 0. These two are dual spaces. So that's why you just integrate 1, and the virtual dimension is 0. Yeah,
Any questions?
So the 1, 2 type can also define symmetric theory.
that's a symmetric.
Symmetric construction. So you get critical locus, and then you get
Yeah, that's symplectic structure.
so that's like also.
Well, it's very easy in terms of this L-infinity structure. There's nothing. It's just so-called cyclic. You have an invariant pair. That's it. Right? That corresponds to the symmetric constructions.
The question is, can you define the floor field?
Yeah. Floor theory?
Transcendent floor field.
Schild-Simons. What's Schild-Simons?
The infinite homological.
That I don't know. I don't know what is the.
Categorical.
So, can you recall first?
So actually I work on. I'm actually working on it. So. So there's this. Are you talking about this forward strip? Joyce did in the case of Calabian's rituals?
That's quite complex.
Yeah. So in the real case, it's more complicated. So you don't get locally it is critical locus of real analytic functions, but you don't get perverse shifts if it's real analytic. It's constructible shifts. And then you have to. It's not a billion category, so it's very. It's not difficult. It's not easy to prove to a global object.
And can you recall if you have an A-infinity algebra, what is the L-infinity algebra associated with it?
It's just the usual thing. So the symmetrization. Right? So when you have an associative algebra, you have AB times B. You get a Lie algebra by taking Lie bracket. So if you have an A-infinity algebra, so you have sigma 1. Also sigma A.
And
Permutations.
what does it capture?
Huh?
What does it capture?
It captures the commutative part, I mean the symmetric part, just like here, right? It's just the commutator part.
Right. But
So Yeah, it's less information.
But L-infinity is really what you capture the information.
Yeah. For deformation, I mean, it depends. In yesterday's talk, you could have not committed deformation. Right?
So does it capture flow theory, or it seems that flow theory seldom talk about use this operator?
Yeah, for the, if you want to say obstruction, obstructive is weakly obstructed or obstructed, it's L-infinity is okay. Because the Monocartan equation is itself symmetric. Whereas when you symmetrize Monocartan equation, it's still Monocartan.
Does that figure again?